Good morning, dear students. Welcome back to physics class. Today, I would like to introduce a new chapter which is mechanical properties of fluids. For today's class, I am going to discuss mainly on three topics which are A. Pressure due to a fluid column, B. Pascal's law, and C. Variation of pressure with depth. This chapter tells about mechanical properties of fluids. Do you know what are fluids? Fluids are substances which are capable of flowing. They do not have any shape of their own. For example, water which does not have its own shape, but it takes the shape of its container. When we pour water in a tumbler, it takes the shape of the tumbler. You know, water is a liquid substance. It is an example of fluid. Both liquids and gases are collectively called as fluids as they are capable of flowing. Volume of solids, liquids, and gas depends on the stress or pressure acting on it. In this chapter, let us discuss on how does the applied force on the fluids affects their internal properties. You should know fluids offer very little resistance to shear stress. First topic from this chapter is pressure due to a fluid column. Now, let us discuss on two basic characteristics of fluids which are pressure and density. First, I am going to focus on the basic characteristic of fluid, pressure. Can you say what is pressure? Pressure is force per unit area. Pressure is equal to force divided by area. Let me point out one live situation. A sharp needle, when pressed against our skin, can pierce it. But when a blunt object with a wider contact area, say back of a pencil, is pressed against the skin with the same force, it remains intact. This convinces you lesser the area of contact, greater is the pressure, and vice versa. Both the force and its coverage area are depend on pressure. So, there are two factors which determine the magnitude of the pressure. First one is magnitude of force applied, and second one is area of contact. You have to note these points. First, greater the force applied, greater is the pressure, and lower the force applied, lower is the pressure. And second, greater the area of contact, less is the pressure, and lower the area of contact, more is the pressure. Then, what is fluid pressure? It is normal force or perpendicular force exerted by fluid per unit area. This force acts perpendicularly to the surface of contact. Consider a body submerged in water. Force is exerted by the water perpendicular to the surface of the submerged body. The force acted on the body is only the perpendicular force. There is no parallel acting force on the body. What is its justification? If there were a component of force parallel to the surface, the object will also exert a force on the water parallel to it in accordance with Newton's third law of motion, which states that for every action there is an equal and opposite reaction. This opposite force will cause the motion of water along the horizontal direction. Since the fluid is at rest, this cannot happen. Therefore, we can say that the force is applied perpendicularly to the contact surface of the submerged body. At a point can be measurable. Let us see how can measure the fluid pressure. An idealized form of one such pressure measuring device is shown in given figure. It consists of an evacuated chamber with a spring that is calibrated to measure the force acting on the piston. This device is placed at a point inside the fluid. The inward force exerted by the fluid on the piston is balanced by the outward spring force, and it is measured. Let F be the magnitude of this normal force acted on the piston of area of contact, capital letter A. Let PAV be the average pressure. Then PAV can be written as PAV is equal to F by A. In principle, piston area is made arbitrarily small. Then what should be the pressure? It is P is equal to limit delta A tends to 0 delta F by delta A. Here we have used the limiting condition as delta A is approaching to 0. Pressure is a scalar quantity because the force per unit area is not a vector force, but it is the component of force normal to the area. What is its dimensional formula? It is mL raised to minus 1 T raised to minus 2. What is its SI unit? Its unit is Newton per meter square or Pascal. 1 Pascal is equal to 1 Newton per meter square. A common unit of pressure is the atmosphere, which is denoted by ATM. It is the pressure exerted by the atmosphere at the sea level. 1 atmosphere is equal to 1.013 into 10 to the power of 5 Pascal. It is the common atmospheric pressure. Second basic quantity of fluids is the density. It is denoted by the Greek letter rho. What is density of fluid? It is the ratio of mass to volume of fluid. For a fluid of mass m occupying volume v, the density rho is equal to mass divided by volume, which is equal to m by v. In the fluids, liquid substance is largely incompressible than gaseous substance, so its density is nearly constant at all pressures. The density of water at 4 degrees Celsius, which is equivalent to 277 Kelvin, is equal to 1.0 into 10 to the power of 3 kilogram per meter cube, which is equivalent to 1 gram per centimeter cube in CGS system. Then what should be the relative density of a substance? It is the ratio of density of substance to density of water at 4 degrees Celsius. Why does it use the temperature condition of water as 4 degrees Celsius? Because water has maximum density at 4 degrees Celsius. Relative density is a dimensionless positive scalar quantity. For example, the relative density of aluminium is 2.7. It means that the density of aluminium is 2.7 times more the density of water. Then the density of aluminium is equal to 2.7 into 10 the power of 3 kilogram per meter cube. On next, I am going to introduce you Pascal's law. French scientist Blaise Pascal noticed that the pressure in a fluid at rest is the same at all points if they are at the same height. The result of his observation is given in the form of Pascal's law. What is Pascal's law? Pascal's law states that if the pressure is applied to uniform fluids that are confined, the fluids will then transmit the same pressure in all directions at the same rate. Pascal's law holds good only for uniform fluids. For example, consider a vessel filled with water which is uniform throughout, as there is only one type of fluid, which is water. Consider another vessel which has both oil and water. Then it is not uniform because it has two different fluids. Fluid should be confined, meaning fluid is present within region in space. It is not allowed to spread. For example, a balloon filled with water, and when you press it hard against the wall, you will see that the shape of the balloon changes. This is because if you apply the force on the balloon, the pressure is exerted on the water. So, as water is uniform fluid, it is confined within the balloon and is not allowed to spread. On applying the pressure, it is transmitted in all other directions. Another example is, consider a vessel of circular shape filled with water which has 4 openings, and in the ender openings 4 pistons are attached. Apply force on the first piston. This piston will move inward and all other pistons will move outwards. This happens because when this piston moves inwards, the pressure is exerted on the water. Water transmits this pressure in all directions. So, the other pistons, except A, moves at the same speed, which shows that water has exerted pressure in all the directions. Which is in equilibrium, the pressure is same at all points in a horizontal plane. This means that there is no net force acting on the fluid. The pressure is same at all the points. A fluid can move only due to the pressure difference. It means that fluid will always move from a point which is at a higher pressure to another point which is at a lower pressure. Now, let you study about how is the variation of the fluid pressure with respect to the depth. Consider a cylindrical element of fluid having area of cross-section capital letter A and height h. As the fluid is at rest, the resultant horizontal forces should be 0 and the resultant vertical forces should balance the weight of the element. Let us consider 2 points 1 and 2 of the cylindrical element where the point 1 is at the height h above the point 2. Let P1 and P2 be the pressures at the points 1 and 2 respectively. Let us see what are the forces acting along the vertical direction. Force at the position 1 is perpendicular to the cross-section area A is F1 is equal to P1A. Similarly, force acted at the position 2 perpendicular to the cross-section area A is F2 is equal to P2A. You know that pressure is force per unit area. Then force is equal to pressure into area. Then what should be the total force or net force acted on the cylindrical element of fluid? It is F net is equal to minus F1 plus F2, as F1 is acting along the negative y-axis, so it is the negative, and F2 is acting along the positive y-axis, so it is the positive force. Then F net is equal to P2A minus P1A. It is equal to P2 minus P1 into A, which is the expression 1. I pointed out earlier the net force acted on this cylindrical element will be balanced by the weight of this element of mass m. So, under equilibrium condition, the net force acted on the cylindrical element F net is equal to mass into acceleration due to gravity. It is mg, which is the weight of the cylindrical element. Therefore, F net is equal to rho Vg. Since mass is equal to rho V, as rho is equal to mass per unit volume, where rho be the density and V be the volume of the fluid. So, F net is equal to rho h Ag, where V is equal to height into area of cross-section of the cylindrical element. Then F net is equal to rho h Ag, which is the expression 2. From the expressions 1 and 2, we get P2 minus P1 into A is equal to rho h Ag. Then P2 minus P1 is equal to rho hg or h rho g, which is the expression 3. From this expression, you can see that the difference in the pressures P2 minus P1 is dependent on the height of the cylindrical element of the fluid or the height of the cylindrical fluid element H. Consider the top of the cylindrical element exposed to air. Then P1 is equal to PA, which is equal to atmospheric pressure. So, from the expression 3, we can write P2 is equal to PA plus H rho g, which is the expression 4. You have to see that the pressure P at depth below the surface of a liquid open to the atmosphere is greater than atmospheric pressure by an amount H rho g. This pressure is independent of area of cross-section or base area and the shape of the container. And the excess pressure P minus PA at depth H is called a gauge pressure at that point. The gauge pressure P minus PA is equal to H rho g, which is obtained from the expression 4. The homework questions are given in this slide. Please you have to work out these question answers by today itself. Okay, thank you. Have a nice day.